Now today we will study first fundamental theorem on isomorphism of vector spaces. So let us talk about its statement. Statement is if VF and WF are vector species over a field F and T from V to W is a linear is a linear is a onto linear map is a onto linear transformation map or transformation with kernel 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 of T is equal to K, then V by K is isomorphic to W. This is what we have to prove. So what we have two vector spaces. One vector space is this, one vector space is this. They are on the field F. And there is a map. There is a linear transformation. This is an onto linear transformation. Linear transformation with kernel of T is equal to K. Then we see that V by K is isomorphic to W. That V kernel K is isomorphic to W. This is what we have to prove. So let us talk about its proof. The proof is proof. Firstly, we will define the kernel. Firstly, we define the kernel of T. So kernel of T is a set. Kernel of T is a set of all the elements of the domain which are mapped to 0 of W, because T is a map from V to W. So those maps which are mapping to 0 of W, that constitutes those elements constitutes the kernel of T. So this is what the kernel of T is. Now we will define a map. So define a map Z from V by K to W by, this is Z of, this is X plus K is equal to T of X for all X plus K belongs to B by K and X belongs to V. So this is the value, this is the definition of uh, this quotient space. So these are the elements of quotient space. So first of all, we will check whether the map is well defined or not. Now, first of all, we will check the map is well defined. So let's see. Z is well defined. Well defined. Let's see how it is. Now what happens that as K plus X belongs to W, V by K, sorry, X plus K. Whether you write K right or left coset, one and the same thing. If as X plus K belongs to V by W, this implies X belongs to V and because T is a map from B to W and is an onto map. But this is a K here. So this is just a moment. This X plus K belongs to B by W. This implies that X belongs to B. Okay. This is not W. This is K. This X belongs to V. Now we can see that this Tx under T is a map from B to W. This is the onto map. So this X belongs to W. We are taking X here. So after putting T over it, so this is coming here Tx. This belongs to W. This means that Tx belongs to W. One thing is clear that if we are taking this x plus k in v by k, this x belongs to v. Then correspondingly using the map structure of t, we can see that tx belongs to this w. This further implies that because tx is equal to nothing but z of x plus what? This is x plus k. So x plus k belongs to w. So what we are seeing? We are seeing uh, z from v by k to w. So we have taken here x plus k element and we are putting this element in w, that is tx, because we have seen here that this tx belongs to w. So for x plus b, x plus k is associated to tx. So this map is defined like this. Now we will see that whether the map is well defined or not. So what we do, we take two elements, make them equal, and see that whether they are going to the same image or not. They are going to the unique image or not. So we will see that whether this any two elements, sorry, any element is having a unique image or not. Let us check. So because we no domain is here, domain is v by k, so we can take two elements here. Let x plus k and y plus k belongs to v by k. So these are the elements of such that elements of the domain such that these two elements are equal. We have to say that every element is a unique image. So this is the way to show this. This is kernel. Fine. Now what happens? This is the coset form. So we can write x minus y belongs to k. That is a kernel of t. That is kernel of t. Now this is equal to kernel of t. Now this implies what? This implies that t of x minus y, this goes to 0. 0 of what? W. Right? So because t is linear, we can write this way. T of x minus t of y is equal to 0. So we have got t of x minus t of y is equal to 0. Now simplifying, t of x is equal to t of y, and using the back definition, because we know that z is a map from v to w and z of x plus k, this is nothing but tx. So we are just using the back definition, and this is going to come as z of x plus k is equal to z of y plus k. Fine. So we have shown that so we have shown that if we are taking two elements equal, if their two elements are equal in the domain, then their images are same. That means that means that means every element element this is v by k actually. Every element in v by k has a unique image. So we can see that the image is unique. This is the basic of this map. So this means map Z from V by K to W is well defined. So map is well defined. We can move further. So next we will show that. Next we will show that. We'll show that Z map V from K to W given by Z of x plus K is equal to T of x is 1 1 on 2 and linear map, linear transformation. Fine. We will show this or homomorphism or vector homomorphism. You can say that. So these are the three things: 1 1 on 2 and linear transformation we have to show. So let us show. Now, z of x plus k, this is nothing but t of x, where z is a map from v by k to w. So we have to show that z is, first thing, z is a homomorphism or linear transformation or a linear map, linear transformation. Fine. We will show this. So we will take two elements in the domain. Let x plus k, y plus k in v by k and alpha belongs to field. So now we'll see their sum or their product, scalar product. Let's see x plus k plus y plus k. Let's see how, whether it preserves or not. Addition is preserved or not under this map. So let us see. This is going to come as, by definition of cosets, adding these representatives x plus k. This is what we are getting. Now, sorry, because because we are taking here z. So we are taking here z. So we are applying here z. We are working on the z now. We have to show that z is a linear transformation. So z is equal to this. Now, this z can be written as, by definition, because this is a definition of this. So this is the representative. We have to take t of x plus y. Now t is linear. T is linear. So we can write t of x plus t of y. This is further can be written as, so using the back definition, this is going to be z of x plus k plus z of y plus k. So we have shown that, therefore, z of x plus k plus y plus k, this is equal to z of x plus k plus z of y plus k. So this is what we have shown. So therefore, z is a linear. So one more thing we have to show that for linearity. Next we show that, next we will show that t of alpha x plus k, z of this, z of is equal to alpha t of z of x plus k. This is what we have to show. Now, now t of z of alpha x plus k, this is equal to z of alpha x plus k, and this is equal to, by definition, because z is a map from v by k to w, z of x plus k is equal to t of x. So by using this definition, we can write this t of alpha x, because t is linear, linear map. So we can write this is alpha t of x. Then again using the back definition. So this is going to come as alpha z of x plus k. This is what we are getting. So we have proved that this holds. Therefore, z of alpha x plus k is equal to alpha times z of x plus k. Therefore, z is a linear transformation. Transformation. Fine. So z is a linear transformation because this property holds and this property also holds. These two properties, we can say that z is a linear transformation. Next, we will show that z is a next we will show that z is 1 1. So z is 1 1. Let us talk about this. Now t is, let us write the map first. Z is a map from v to v by k to w. Z of x plus k is equal to t of x. Right? So we'll show that this is a 1 1 map. Let x plus k, y plus k belongs to v by k. Right? Say that z of x plus k is equal to z of y plus k. Fine. So by definition, this is equal to tx. So this is tx and this is equal to t of y. So we can write this t of x minus t of y, and this is 0. This is a 0 of w. This is 0 of w. So this is a t is a linear map. So we can write t of x minus y is equal to 0. And this gives you, this implies x minus y belongs to kernel of t, that is k. So we are getting, so we have got x minus y belongs to k. Now this can be done as x plus k is equal to y plus k. Property of the this cosets, because if x minus y belongs to x plus k is equal to y plus k if and only if x minus y belongs to k. Actually, this is a identity when the binary operation is plus. For multiplication, we have already done x of h is equal to y of h if and only if x y inverse belongs to h. So this is the property we have used for addition of binary operation. So this is what it is, and this is how it is going. So we have taken z is equal to z x plus k is equal to z of y plus k. We have shown that x plus k is equal to y plus k. So elements of the domain. So so what we have shown, therefore t of z of x plus k is equal to z of y plus k implies x plus k is equal to y plus k. This means that z is 1 1 because if images are same, then the domain elements are same, or we can say that every element goes to a unique element. Every element is associated with a unique element. That is, every element of v by k is associated with a unique element of w. Unique element of this goes to unique element of w. So this is 1 1. Now we will talk about the onto. Next we will show next z is onto. Fine. So we will prove that z is onto. Let's show that. Now t from v by k to w. This is a z actually. Z from v by k to w given by t of z of x plus k is equal to T of x. This is the map where x belongs to V and x plus k belongs to V by k. So we have to show that this is an onto map, and we will show that we'll take y belong here in W, and corresponding there is x plus k belongs to b by k, say that T of x plus k is equal to y. This is what we have to show. So we will take y belongs to what? W. Let करते let y belongs to W. So now T from V to W is an onto map, is an onto map. This implies that eh, we have taken y here. So there is y here in W. So corresponding to y, we can get x here because this is an onto map. Therefore, for therefore for y belongs to W, there exists x belongs to V such that T of x is equal to y. So we have taken T of x is equal to y. So this y is in W. So we have shown that we are getting a point Tx in y corresponding to x. So corresponding to this, we got x. Therefore, this x belongs to V. This implies that x plus k, this is going to be coset. This belongs to V by k. This means that for y belongs to W, for y belongs to W, we are getting a x plus k in b by k like this. So therefore we can write, therefore for all y belongs to W, there exists x plus k belongs to V by W such that z of x plus k, if I apply z of x plus k. So z of x plus k is going to what? Z of x plus k is by definition Tx, and this Tx is what? This Tx is nothing but this y. So we have shown that is equal to y. So for every y belongs to T is from z is from V by k to W. For every y belongs to here, there exists x plus k belongs to V by k such that T z of x plus k is equal to T, T of x or is equal to y. Or one may say that T of x plus k is equal to y. So we have proved this for every y in W, there is some x plus k, so that when the z is applied on this, z of x plus k, this is equal to Tx and this is equal to y. So this means that z is onto map. So we have shown that, therefore, z from V by k to W is a linear transformation, or second, this is 1, 1. Third, we have proved that this is onto. This means that z is z from V by W, sorry, B by K kernel to W is a is an isomorphism. Fine. This is an isomorphism. If this is an isomorphism, so we have proved that B by K to W is an isomorphism. This implies that B by K is isomorphic to W. So this is what we have to prove. This is the statement of first fundamental theorem. Fundamental theorem. This is how we have to prove that this is a V by K is isomorphic to V by K is isomorphic to W. So this is very easy. So please go through this. Thank you.